Hello everyone, let's take a look at our next problem. So this is another problem submitted by a viewer. The topic is double minimum integral. And it says, given 0 less than a less than or equal to b, solve the integral from 0 to a of the integral from 0 to b of the minimum of x and y dx dy. Okay, there's a follow-up. There's a follow-up of this that sort of generalizes the problem, but I'll just work on the two-dimensional version. So let me write down exactly the integral that we're given here. Okay, so it's a two-dimensional integral over a rectangular region, and the function we're integrating is a function of two variables, which is just the minimum of the two variables, x and y. I'm thinking to make sense of this, drawing a diagram will help a lot so we can see the exact region we're integrating over. And of course, this function x, y, the value of the function is only going to depend on the region of the plane we're in, where the region is going to be divided by a diagonal line. So let me draw a diagram to show what it is I'm thinking here when I say this. Okay, so y goes from 0 to a, and a is smaller than b, so I'll just label arbitrarily a couple points here like this. So this is the region that we're integrating over. But the function itself, I'm not sketching the function here. What I'm doing is I'm sketching the region over where the function changes values, basically. So we're integrating over this pink rectangle, the outline of the pink rectangle. Here, the value of the function is the minimum of x and y, which is x. And over here, the value of the function is the minimum of x and y, which will be y. So maybe it'll be easy to simply split this up into two integrals. I'm thinking I'll integrate over that region. Actually, maybe another way to do this. Okay, so new thought. The minimum of x and y we can write this as let me think for a sec. So what I'm thinking is it might be easy to integrate an easier function over the entire rectangular region, and then subtract something which is integrated over this smaller triangle so that it kind of flips the value into what it should be. So the minimum of x and y is equal to y, if y is less than or equal to x, of course. Or it's equal to y minus x if y is greater than or equal to x. And so I'm thinking here, we integrate this function, we just integrate y over the entire rectangle. And then, oh, we're not going to want to subtract this. We're going to want to subtract, let me think for a second here. Oh yeah, okay, so we'll integrate y over the entire rectangle, and that's like integrating that in the like sort of correctly in the bottom right region, and then but also integrating that in the left region. And so what we'll need to subtract is that, but that doesn't seem any harder or easier here than splitting it up into two integrals. So maybe it will be easier to just split it into two integrals. Yeah, okay, so let me do it that way. I'll call this region, the integral for that region will be I1, and the integral for this region will be I2. So I1 is going to be a double integral. In that region, when y is bigger than x, we're integrating x, dx, dy. It might be easier to, depending on the bounds. I might interchange the order of the integral, but let me think what's going to go on here. Okay, so that should be, I'm pretty sure that's the correct value of I1, right? X at any value of y, x goes from 0 up to that value of y, and y itself goes from 0 to a. And in this region, x is less than y, and so we're integrating x. Okay, so we can compute this integral pretty easily. We'll just do it from the inside out. So antiderivative of x is x squared over 2, and we have to evaluate this 0 to y, which gives us the integral from 0 to a of y squared over 2 dy, which is the integral, which is y cubed over 6 evaluated at a, which is just a cubed over 6. So this is I1. And then I2 we're going to do in a similar way. In fact, maybe instead of calling that I2, that'll be I2 and this will be I3. Because I was going to break up the integral that way anyway. So I2 is a double integral. Y goes from 0 to x, and x goes from 0 to a in this case, and we're integrating y dy dx. In fact, this is going to give us the same value as I1, right? It's symmetric. The integral of our function over the upper triangle is the same as the integral over a function over the lower triangle, because the roles of x and y are completely interchanged. So this is a cubed over 6. But then I3 is a double integral of, so we're going to, this value here is of course a. So x goes from a to b, y goes from 0 to a, dy dx, and we're integrating y. So this is what, I'm going to do the substitution immediately. So this is a squared over 2 dx. And this gives us a squared over 2 times b minus a. Okay, so the entire integral is I1 plus I2 plus I3. So this gives us a cubed over 3 plus a squared over 2 times b minus a. Is there a nice simplification of this? So I get a cubed over 3 minus a cubed over 2 plus a squared b over 2, which is equal to negative a cubed over 6 plus a squared b over 2. I mean, yeah, maybe you can simplify this more, but I don't see any need to. I'm just going to spend a minute sort of going over. I didn't end up using this. I didn't end up using that anywhere. I'm just going to think for a second to see if I can catch any mistakes I may have made. Yeah, I think this is correct. I didn't see anything I may have messed up. So I'm going to read the slightly harder version of the problem that was also submitted by the viewer. It's basically the exact same question, except we generalized to 3 dimensions. So I can just write out what we're asked to compute. So we introduce a third variable now. We have a 3-dimensional function, or a function of 3 variables, the minimum of x, y, and z. And we're just integrating again over a rectangular region. So now it's a lot harder to draw a picture and visualize the domains that we're integrating over. Would that be a disaster, trying to draw a 3-dimensional thing here? So what I'm considering doing for this is evaluating the double integral in the inner part. So kind of like basically fixing z, fix z to be an arbitrary value, and compute the integral in the inner part. That will of course end up being something that depends on z, and then integrate that. But of course, the way it depends on z is going to be kind of bizarre, depending on... Oh man. We did have this nice thing that happened up here, that I1 and I2 were equal. And of course, something similar to that is going to happen in the 3-dimensional version, where there are going to be symmetries and things will be equal. But then we'll have to sort of figure out exactly what the extra region is. Okay, so I'm gonna follow through with the idea of trying to evaluate that. So I'm going to fix z to be some value. I know that, so z, a is the smallest of these parameters, so z is always between 0 and a, so I never have to worry about z being greater than a, or therefore I don't have to worry about it being greater than b or greater than c. I'm going to evaluate that integral, see what I get the way it depends on z, and then just integrate this thing as a function of z. So what I'm doing here, I've just redrawn basically the picture we had in the 2-dimensional version. I'm imagining that z is some fixed value, and then here in the new I1 region, x is less than y, and so the minimum of the 3 variables is never going to be equal to y. It'll either be equal to x or z, whichever one is smaller. So I put this in here. And then I2 will be similar, and I3 I'll figure out when we get there. So in this integral, the first one, when x is less than z, the minimum of x and z is x. So I've divided the integral into 2 regions. The original integral goes from 0 to y. I'm going to write this as an integral from 0 to z plus from z to y, where the thing we integrate changes. Okay, so this is the I1 for the inner integral. Now let's go ahead and compute I2. So for I2, again, y is less than x in here. So the minimum of all three variables can never be x. It'll either be y or z. Y goes from 0 to x, and x goes from 0 to b. This should give us the same quantity as I1 again, right? I don't see why it wouldn't. I've literally just interchanged x's and y's in the symbols. Okay, so this is also going to be equal to zb times b minus z over 2. Okay, and I3 is an integral from, it's an integral from b to c, integral from 0 to b. In this region down here, the minimum, so y is less than x, so the minimum can never be x. So we again have the minimum of y and z. dy dx. Okay. Now this integral from 0 to b, I'm going to split that up into an integral from 0. So this is y, the dummy variable y is now changing from 0 to b. I'll write this as an integral from 0 to z dy plus an integral from z to b dy. And so when y is small, we're integrating y here. When y is large, we're integrating z. So this is just going to give us z plus b minus z. Okay, perhaps I should have seen this coming. So this just gives us b times c minus b. Okay, so I1 plus I2 plus I3 is zb times b minus z plus b c minus b. Okay, and everything here is positive, right? The function we're integrating is positive everywhere. I've made the comment already that z is always less than b, and we know c is greater than b, so this is all positive. This is good. And what I need to do now is integrate this as z goes from 0 to c. No, 0 to a. Does this thing simplify in any way? I don't know, maybe there's some factoring. I'm tempted to write the a times b times c as one term. I'm a little confused as to why it appears that certain dimensions don't work. I suspect I have a mistake. Right? This is all of our total dimension is 4, right? The total exponent there is 4, same with here, but here it's only 3. Okay, let me spend some time going back and see if I can find an error somewhere. My computation for I3 doesn't look correct. So this should be z squared over 2 plus z times b minus z, all that dx. So this is the integral from b to c of zb minus z squared over 2 dx, which is zb c minus b minus z squared over 2, c minus b. Okay. I don't want to, I'm just going to redo everything below. I don't want to have to keep track of tracking that single mistake. So I think this is correct. I admit I'm definitely not seeing a pattern in what's going on. So I mean, the third part of the question submitted by the viewer is to derive a general formula for this kind of thing for n variables, and I'm not seeing a pattern. Maybe the way to do this would be to assume that a, b, and c are equal, and then look at like the excess region, or you know, derive the formula when a, b, and c are equal. That might be more doable. And then, yeah, I'm not sure. I mean, my instinct for stuff like this often is to just sort of start doing the computation, and I wouldn't quite call it a brute force approach, but that's more or less just what I did. And it'll get the right answer, but it may be very difficult to generalize the answer. So I'm not sure if there's some clever thing we could do that makes all the computations kind of just come out more nicely. I think for now, you know, to make this video reasonable length, I'm going to call this, I'll call it an end to this problem for now. I'm mostly confident in the answers that I gave for the first two parts of the question. It's possible that I made some arithmetic mistakes or integration mistakes, but I think my approach was correct, although maybe not the most elegant. It's certainly going to be more difficult to generalize this to higher dimensions. If I find a mistake in what I did, I'll include something in the description. And if I have any ideas, you know, as I think about this in the back of my mind, then maybe I'll make up a follow-up video for the more general version. But for now, thanks for watching.